just don't stop working. You know, generally, I'll continue to read for myself. You know, maybe I'll pick up a book on game theory and decide that I want to teach myself game theory. This is the time when I'll grade papers, I'll grade labs, I'll grade quizzes, I'll grade exams, because I try to keep my research separate from my teaching responsibilities, because when I'm in lab, it's all about getting research done. When I go home, I'll deal with grading quizzes, developing solutions to exams. Not every instructor will give you a solution to a midterm exam or a final exam, so you have to do it, which means you kind of have to be confident about the area that you're teaching. Or I'll work on my homework that I have to do. You know, as a student, as I take classes, I still have to do homework. But what is this? What does the research really entail? So I came up with an abridged list of what I do at any given time. So much of it is spent reading papers. A lot of it is spent reading papers, like reading technical papers that have been published in the IEEE. To be able to read these papers, you have to have an understanding of the research area that you're in. So not only the fundamentals of the field, say digital signal processing maybe, but if you're trying to read these advanced papers on digital signal processing, you need to know everything that's going on around them to be able to understand what's going on in the paper. So you'll spend a lot of time reading papers, reviewing papers for conferences and journals that might get accepted, writing code, verifying code, all about, you know, maybe developing new methods, and then, you know, doing all the data analysis associated with implementing the methods and testing them, and the statistical analysis associated with them. And then once you have this method developed, you've analyzed the data, you start writing conference papers and journal papers, and if they get accepted, you have to get the material ready to go to the conference. And this is all research-based. You have to deal with the lab meetings. You have to have meetings with your advisors. Usually I meet with my advisor 2 to 3 days a week to show them results. So that's generally, you have to be doing work every day in lab, or else that meeting is going to be like, well, what'd you get done yesterday? And you don't ever want to be like, well, I don't know what to do. You want to be on top of your game. Another part is dealing with students. So as a teaching assistant, I have to hold office hours, I have to grade, and I have to deal with students' questions regarding their grades and why they got what they got. And a whole bunch of other stuff. And then on top of that, I have to go to class as well. So I guess the point to take away here is there's a lot of different things involved in research, but a lot of it is just expanding your education on what you know about a particular area that you're focusing on. So if you're focusing on digital signal processing, you're reading and reviewing papers in that specific area. You're writing code to solve problems in that specific area. You're preparing and analyzing data from the methods that you've developed. So it could be a number of different things, but it could be also a lot of other things I didn't mention on here. So here's a few tips that I actually pulled out of. So Mark Drentz and Hannah Wallach have, I think, a really, really good paper on what it takes to be a successful grad student in CS, and in particular natural language processing. But I think across the board, these bullet points go across engineering, any other field that you'd be looking at. So particularly for the PhD, research is always going to be number one. And with the Masters of Science, it's going to be heavier, but research is always number one. So it's not about classes at this point. You want to talk to other students. You want to know what they're working on. And you know, how does your level of work compare to their level of work, or how's their workload compared to your workload? And it's good to get an idea about what other students are researching as well, because it may help you in your own research along the way. Everyone works differently, and I think one of the things I was told when I came to grad school is that research doesn't necessarily start at 8 o'clock in the morning. A lot of people think of having like an 8 to 5 job. There's people that may come in at 2 o'clock in the afternoon, but they'll stay later because they work better in the evenings than they do in the morning. So it's important in terms of getting research done, what time works best for you to actually be most productive, which kind of keeps into play of keeping a regular schedule, as I have one for myself. Prioritize, you guys already get this from your senior project, and making action items. This is one of the more important ones, I think, about grad school, is when you make action items, you want to, you have something that you want to do, and you want to continue to make these as you go along throughout your degree. Generally, something is wrong if you're waiting for your advisor to tell you what to do. You always want to be the one who's in control of your research, and you don't want your advisor to be the one who's holding your hand and pulling you along. Because at the end of the day, when you graduate, you should know more about the area than your advisor actually does, which I think is definitely true in every case study. You want to keep a log of everything you do. I use Evernote. Getting things done, that's self-explanatory. And if you're working day in and day out, it's important once in a while to keep a social life going, because as I said, if you're doing that schedule every single day, it becomes tiring and it's easy to burn out, so it's important to get out once in a while. And in research, it's okay to get stuck once in a while because you're working on problems that it's not clear to see the end of it. So it's easy to get stuck in maybe some mathematical set of details that you're just not able to get by, and you just need a boost from somebody else to get you by. So it's okay to get stuck, but it's even more important that you learn from your mistakes if you do get stuck. So I have, I think, 5 sets of suggestions if you're thinking about grad school. So I tried to put these together and kind of keep them kind of condensed, but if you have any questions, let me know. So I think the biggest one is hands down mathematics. You have to be good, and you have to have a diverse set of math skills. When I was here, I took Calc 1, Calc 2, Calc 3, ordinary differential equations, linear algebra, probability and statistics, and I think that's all I took here. But
I have a quick question here.
Yeah.
When you took linear algebra here, how difficult a course would you say that was compared to other linear algebra courses?
I didn't think it was too difficult. Linear algebra can be difficult depending on how it's taught.
Yes.
I think the most difficult part that I had about linear algebra, and I will say this, even in like the large schools like Drexel and engineering, you'll talk about, does anybody know what the eigenvalue problem is? I think a lot of people know what it is. Like they know, like if I asked somebody to write down the characteristic equation, they could do it. But if I asked you, well, really, what does it mean to have an eigenvector? What do the eigenvalues actually mean? It's like they get fumbled. And that's, I think, topics you don't see towards like graduate level courses. But I don't think it's that hard.
Maybe a better question would be the linear algebra course was sufficient for you.
Yeah.
Okay.
Yeah, I mean, you get everything you need.
Yeah.
So, and what I mean by linear algebra is basic linear algebra to be able to go into grad school. So you want to know about inner products, matrix inversion, the eigenvalue problem, determinants. What does the determinant mean? What do the eigenvalues mean? What does an eigenvector mean? All this stuff is very important. And it's one of those things that when you take higher level control systems, image processing, signal processing, machine learning theory, you have to have a background in linear algebra to be able to get by. So, and I think all these courses are offered here, and I think you pick most of them up along the way, right, to get the degree. So math cannot be understated enough of how much it is needed in graduate school. Second would be programming. Being a good and efficient programmer is a skill that not everybody has. And I think it pays off for you if you are a good and efficient programmer. And it's not just being able to program in one language, but having a general idea of how to program in any language. So understanding object-oriented programming is really important. Understanding what a class is, understanding what an abstract class is, understanding what an interface is, and what these mean in terms of a software project is all very important. And learning to write scripts, I think, is a very powerful thing, whether the scripts be in MATLAB or some program like Python. Learning at least one scripting language is a good thing. MATLAB is generally used in academia very, very heavily, more so than C, C++, Java, Python, Perl, but all of those other languages are very important. So knowing at least 2 or 3 of those may help you get ahead, depending on what you're working on. So another thing to maybe look at is research on your own. And it's something to look at in baby steps. You don't start out by trying to prove some massive theorem about something. You start out by doing something small. So if your senior project would call for like an automated decision to be made about something, like maybe a pass-fail, Maybe you want to look at some machine learning algorithm, some detection and estimation algorithm, using like the Naylor-Pearson lemma to determine whether you reject or fail a test. So math, programming, and a little bit of research to get you started in grad school. And the last set is intentions. So at the end of the day, you really have to be motivated about what it is that you want to do. Okay? So just because you're book smart doesn't mean you're necessarily going to be successful in research, but the opposite isn't true either. You want to be in a research field and you want an advisor that has similar goals to you. So if you're going to grad school and the only funding available is for nanotechnology and you're interested in signal processing, it's probably not going to be a good fit for you in that lab. You want your advisor and yourself to have similar research goals so that you can both benefit. And if you are going to go to grad school, you should research your future advisor actually pretty early. So research them, go to their website, read some of their papers. It may be a little tough to read at first, but it's not a bad idea to do. And then try to meet them in person if you can. I think a face-to-face meeting with your advisor is much, much better than any type of email transition that you can send between them. And I think one of the biggest things that I see as I grade papers is writing abilities. Usually in undergrad, they're not the best writers in the world. I shouldn't use horrible, but they're not the greatest writers in the world. So I think writing and learning to write well is a skill that is very beneficial, because when you start to write conference papers and journal papers, you have to have very well written English, so your English skills have to be very good, and you have to be able to communicate to the audience that you know what you're talking about in a very clear.
Do you think reading those papers will kind of get you used to the way
Yes.
those things need
Yeah,
to be
and
written?
they're
Because they're written entirely differently than
They're
other
written
things.
entirely differently because, so I'll give you an example. When I write a paper, I assume that there is some level of knowledge that is already, that the reader already has. So I wrote a paper on, it was called Fusion Methods for, I don't remember it. But essentially what we were doing is we were trying to identify speakers in a database, and the problem is that the speech signals that we got were collected from a phone system. And essentially what happened is they used different sessions to record people's just plain written or spoken text. And what would happen is halfway through this study, they changed the phone system used. So, and I know he's laughing back there, but the problem is that if you have this detection algorithm out there and you're feeding these, we were using autocorrelation coefficients, or something derived, Kepstrom, which is way outside we're going to talk about. We were using these Kepstrom coefficients to predict a speaker, but the problem is that if you change the recording equipment, you've changed everything about the channel. So there's like new channel distortion being added. The features that might describe an individual have now changed. So you have this like abrupt change. And we were trying to figure out, well, how do you get robust features to predict on somebody, even if there is a change? And how do you combine multiple experts together to boost the accuracy of the system? Yeah, but I mean, essentially what happens is what I was getting at the end is that it's written in a way that I expect there to be some level of knowledge understood by somebody before I even write the paper. So I don't talk about how the Mel Kepstrom is implemented. I just jump right into Mel Kepstrom and what's happening with it, what we're improving upon it. Yeah, I mean, technical papers are written in a very specific manner. Okay. If you read 2 or 3 of them, you generally get the idea of how they're written. So that's all I really had going on. If you have any questions, you can feel free to email me. You can visit my website and get an idea about what I'm working on at any given time. If you can't remember the website, you can just Google me. I should come up right away.
You come up right away.
I do?
Yep.
Okay.
Google's first.
Google's first. Okay. If you're interested in this how to be a successful grad student, just look around, Google for Mark Drexel. Him and Hannah Wallach have a really nice paper on what it takes to be a successful grad student. And if you're interested, I'd really recommend reading it. It's very good. Okay. Does anyone have any questions?
What are you going to do after you get your PhD, do you think?
I think I'm going for tenure track faculty positions. And as I said before, that's when the work starts. I think the PhD is just something my goal is to be a tenured professor at a university, and the PhD is something I'm getting along the way to get there.
So you heard that. After he gets his PhD, the work starts.
Yeah.
It should be some fun to it too. I mean, it's
It's a lot of fun. I mean, if I wasn't enjoying myself, I wouldn't be able to deal with the 10-hour days every single day. So it's nonstop, but I love what I'm doing, so I have no reason to not do it.
And you always were a pretty hard worker, but when you went on to graduate school, you had to step up to get, it's like you work, like about 18 hours a day now.
Because when I first started, I'd say my linear algebra skills were basic.
Right.
I don't think I was fantastic. I didn't even understand what the implication of the eigenvalue problem was. I didn't have a strong background in probability theory, and I was going into machine learning. If you know anything about machine learning, probability theory and linear algebra are pretty heavy. So I spent a lot of time, so to be able to read those texts, you had to go back and reference books on probability, books on linear algebra, just to be able to get through the main text of what it is that I'm trying to learn. And then once I have the machine learning down, now it's time to move on and actually read some research papers. So it's nonstop. If you're reading a paper and you're reading something about somebody's method and they say, oh, well, we use Blackwell's approachability theorem. Does anyone in here know what Blackwell's approachability theorem is? No. So you have to go and Google it and look it up. And then you can get back to reading the paper and trying to understand what's going on. Yeah.
Where could I go to get a hold of good papers from respective colleges like MIT or on physics or robotics? It
depends on what you want to do. So the IEEE is an amazing resource, but you have to have a subscription, and that's usually expensive. So what I would recommend,
what I'm talking about is
research. So there's been this push in the journal community to go more public access, and there's one major place I would tell you to look, and it's the archives. ARXIV, if you can remember that. It's based out of Cornell.
I got it.
You got it? And they have books, these very, very technical papers on physics, mathematics, various areas inside of mathematics, computer science. So I find myself in here reading learning papers, and all this stuff is open access, so this is going to be fun. Yeah, so all the papers here give you right away. And some of them are published, some of them aren't. But the archives is a very good place, I think, to get started. Now, many of them, depending on what you're looking for, could be very deep in what's being presented in them, as I'm sure this one is, because I saw it had Grep bounds and Markov chains.
So just out of curiosity, so you use MATLAB. Do you use something as simple as Excel, or do you pretty much use MATLAB for everything now?
I use MATLAB for most of, so my two big programming languages are MATLAB and Python. Python, I think, is it's a very nice and easy language to learn. It's very powerful, and there's been this push from the open source community to actually get functionality of MATLAB in Python.
Have you tried any open source MATLAB stuff? I just came
I've tried
across a
Octave,
couple.
but I mean, in my research field, MATLAB has some very nice functionality that's in their toolboxes. I think their neural networks toolbox, the artificial neural networks toolbox, is by far better than anything I've seen from other people that have pushed stuff out. Optimization methods are very good. Yeah.
Could I find papers on neural networks and stuff like that?
Yeah, so if you're interested in neural networks, you just come into this guy, the archives, computer science. This all neural and evolutionary computing is probably where it's going to be. Yeah, so first one, training a feed-forward neural network with artificial bee colony optimization backpropagation method. That could be actually kind of fun because there's like a whole area of optimization methods, like the particle swarm. There's bee colony, there's ant colony. I think there's some fish. I forget what type of fish like that move around. They build together. Yeah. So, any other questions?
One question I have is, because you're an American citizen, do you feel you have an advantage for research dollars? That's kind of my feeling was back 20 years ago when I was doing it.
Maybe some fellowships are good. Like DoD is obviously going to make it for U.S. citizens, and there's a lot of other very prestigious ones that are for U.S. citizens only. But generally, a good student who is a very good researcher is going to get funding.
Right.
You know, whether it's through some outside institution or whether it's as a research and teaching assistant, they'll get funding to do it.
Right.
And the funding, it's, you know, you're not going to live a lavish lifestyle by any means, no matter where you go. But it's enough to give you a stipend, enough to live off of and pay the bills, and it also generally pays for your courses as well.
Okay, I think there's supposed to be a class in here at 5 o'clock, but it's a welding class. Who knows, I didn't hold class, but. Thank you, sir.
Yep.
We're done then. Zach, I got that from Economos. Your names are all listed.
Kind of wild.
You have to tell me that.